In this lecture, we'll be solving compound inequalities involving the connective word OR. Compound inequalities involving the word OR have a solution set that is the set of all elements contained in the solution sets of both inequalities. Therefore, it is the union of the solution sets of the two inequalities. We discussed before that union meant that we're going to take everything from both sets and just put it together. When we're graphing these solved inequalities, we're going to look for any shading. Any shading that came from either inequality will be a part of our solution. Let's solve, graph, and write our solution set in interval and set builder notations. I'm going to solve each inequality individually. The first one, we'll just divide both sides by 3, which gives me x is strictly less than 4. In our second inequality, we'll add 1 to both sides, which gives us x is strictly greater than 6. There's my solve. I want to graph each one of these inequalities on my number line. This first one we'll do in red. X is strictly less than 4. Find 4 on the number line. X is less than 4. Less than, we shade to the left. Since it's a strict inequality, we want to use a parenthesis at 4 to indicate that we're not including it. We graph our other inequality on the same number line. X is strictly greater than 6. We find 6. X is greater than 6. That means we shade to the right. Since it's a strict inequality, we use a parenthesis at 6 to indicate we're not including it. Since this is a compound inequality involving the word OR, we want the union of our solution sets. That means that we're looking for any shading. Any shading, no matter what color it is going to be part of our answer. So all of this that I've shaded in yellow will be our solution set. Writing it in interval notation. Interval notation is used to represent a non-stop range of numbers. For the first time, we have shading that isn't connected. We're going to have to use 2 different pieces of interval notation, one for each unconnected piece of shading. We'll start with the red piece. I have an arrow pointing forever to the left. That means that we're going to start with negative infinity, and then that shading stops at 4 and gets a parenthesis. We have a second piece of shading starting at 6 with a parenthesis, and then it has an arrow to the right, which means we're going forever to the right all the way to infinity. We need to put something in between these 2 pieces of interval notation to indicate that both pieces are part of our solution, and we use a union symbol. You should never ever use an intersection symbol in your interval notation. There's always a better way to write it. So anytime in the future, do not write an intersection symbol with interval notation, only a union symbol. And then our set builder notation always starts the same, the set of all x, such that, and then our condition is our solved inequality. X is strictly less than 4, or x is strictly greater than 6. Please note that the union symbol does not belong in the set builder notation. You should have only words in your set builder notation, which is why we've written OR. Let's try another one. In this next example, I've already solved the inequalities for us. We're really learning how to interpret the solutions in this section. We have x is greater than or equal to -2. We find -2. X is greater than or equal to, we're shading to the right. Since it's or equal to, I use a square bracket at -2. Next, we have X is strictly greater than 1. I find 1 on the number line. X is greater than that, which means I'm shading to the right. And it's a strict inequality, so I use a parenthesis. The connective word is OR, which means that I want the union of the shading, which is the same as any shading at all. I don't care what color it is. I start having shading at -2, and I don't stop having shading as I approach positive infinity. Notice that my yellow shading, which is my solution, is all connected. There's no break as it was in the previous example. Therefore, I should be able to write this as a single piece of interval notation. My yellow shading starts at -2 with a square bracket, and then it has an arrow going to the right, which means I'm going all the way to positive infinity, and infinity always gets a parenthesis. Our set builder notation always starts the same, the set of all x, such that, and we write our solved inequality in here. X is greater than or equal to -2, or x is strictly greater than 1. In this last example, again, I've already solved the inequalities for us. We'll start by graphing them on the number line. X is strictly less than 7. I find 7 on the number line. X is less than that, so I'm shading to the left. It's a strict inequality, therefore we write a parenthesis at 7. X is greater than or equal to 3. I find 3 on the number line. X is greater than or equal to, which means I'm shading to the right. Since it's or equal to, I use a square bracket. The connective word is OR, which means that I want the union of these two solution sets. Union is any shading at all. So I have shading from here, never stops, all the way to here. Notice that it's the entire number line with arrows on either end. So that means all the numbers on the number line. Our interval notation. An arrow pointing to the left means that we are at -infinity, which gets a parentheses. There is no break in that yellow shading. Therefore, I can write this as a single piece of interval notation. As I move to the right, I see that I have an arrow to the right. We're going all the way to positive infinity. Our set builder notation always starts the same, the set of all x, such that x is strictly less than 7, or x is greater than or equal to 3. Now this set builder notation is fine with me. Another way to write this, since we're talking about the entire number line, all real numbers, we could have written the set builder notation, the set of all x, such that x is any real number.